Now we're going to discuss alcohol protecting groups. You should recall that Grignard reagents can act as bases. So if we were trying to do a Grignard reaction with a carboxylic acid, we would end up just deprotonating the carboxylic acid and generating an alkane. If we tried the same reaction with an alcohol, we would just deprotonate the alcohol and generate the alkoxide. This kind of begs the question, what if we actually wanted to use this as our substrate? So what if we wanted to take this alcohol substrate and generate this product, where we have a Grignard reaction on the carbonyl carbon? You would think that if we're adding an ethyl group right here to the carbonyl, then we could use ethyl magnesium bromide, but the problem with this reaction is that we would deprotonate the alkoxide and the reaction would quench. What we can do instead is use a protecting group, which is basically just a temporary functionality that will prevent undesired reactions. So if we're going back to this reaction we just discussed, and we wanted to form this new product with the Grignard reaction, first we would install a protecting group. The problem with this reaction not working is the fact that the alcohol can generate a proton and quench our Grignard reagent. If we add a protecting group, it will transform the alcohol into something else, which no longer has an acidic proton. We can then perform our Grignard reaction without any undesired reactions occurring here. So we will install our new ethyl group and reduce the carbonyl. Then we can remove the protecting group and get our original alcohol back. There are many examples of alcohol protecting groups. One example is a trimethylsilyl ether. Abbreviation for trimethylsilyl is TMS. So if we take an alcohol, we subject it to a reaction with TMS chloride and triethylamine, we can generate a TMS ether. This can easily be removed under acidic conditions. I'll show you the mechanism for this. If we have an alcohol, it can actually perform an SN2-like reaction with a backside attack, even though this is a tertiary substrate. The reason is silicon is much bigger than carbon, so the backside is larger. So once the alcohol comes in here, we have this trimethylsilyl ether with an extra proton. We add in our triethylamine, which can act as a non-nucleophilic base. That will grab this proton and eliminate this positive charge to give us our TMS ether. The hydrolysis of this, the removal of the protecting group, under acidic conditions we can reprotonate that oxygen. This will generate a protonated species. Water can now act as a nucleophile and attack the R group, kicking off this protonated species and eliminating the positive charge. This gives us an extra proton, which can then be used to regenerate our acid. So let's apply this methodology back to our original reaction. If we add TMS chloride and triethylamine to this alcohol substrate, we will generate the TMS ether. We can then proceed with our Grignard reaction to give us the alkoxide here. Notice we haven't had the aqueous workup step, but what's really convenient about this is after we use our acidic workup, we will not only reprotonate the alkoxide, but we will also cleave the TMS group and regenerate our original alcohol. To summarize, protecting groups will temporarily render part of a molecule unreactive, so we don't have unwanted side reactions. TMS ethers are useful as alcohol protecting groups, and they can be deprotected using acidic conditions.